Hello, my name is Nathaniel Kaye, and my topic today is the formation of oil reserves in Venezuela and Trinidad due to wrench faulting. So where in the world is this study taking place? Venezuela is located on the north coast of South America, on the southern edge of the Caribbean Sea. Trinidad is located about 10 miles off of the northeast coast of Venezuela, still on the continental shelf of South America, and it is circled in red on the slide. The first oil was found in the Maracaibo Basin in northwestern Venezuela in 1914, and more oil basins have been found across Venezuela since. The most notable is the Orinoco oil belt in the East Venezuela Basin province, located in a west-southwest to east-southeast direction through the center of the country, stretching all the way to Trinidad. The USGS predicts that it has 513 billion barrels of oil in it, making it by far the largest oil reserve in the world, compared to 265 billion barrels in Saudi Arabia and 165 billion barrels in the Athabasca oil sands in Canada. This region has been a warm climate going back to Pangea and has moved from the equator, where it was during Pangea, slightly north to its current position over the last 250 million years. The continents spread apart from the central location to where they are today, and the warm, habitable Caribbean Sea was formed in the margin between present-day North and South America. During the Pliocene, which occurred from approximately 5.3 to 2.6 million years ago, the East Venezuelan Basin saw many transgression and regression cycles. The figure on the left was taken at the Puy Galeota site located on the southeast side of Trinidad. As you can see, the transition from clays in the late Miocene to the alternating silts and sands of the Pliocene resulted in extremely thick oil deposits, originating in the Cretaceous rocks beneath it. Oil is present in over 10,000 vertical feet of rock throughout this region, with the fine-grained sandstone becoming saturated in oil. That oil comes from the Cretaceous Cruz Formation clays beneath it, and they have risen up throughout the strata to become locked away in this very porous sandstone. The Pleistocene brought a rise in water level, resulting in much finer sediments being deposited, and the clays on top of the strat column act as the lock to keep the oil in this region in the strat column and not escaping up into the atmosphere. The sample taken on the right from East Queens Beach, which is located slightly north of the Puy Galeota sample, also shows the transition from sands to clays during the Pleistocene, resulting in another seal containing natural gas beneath it. While the deposition was occurring on the continental margin, it is also very important to note that the Andes mountain range was forming at the same time, resulting in massive uplift in the western part of the country, peaks reaching in the thousands of meters in the border with Colombia. The results of uplift in the surrounding landscape, and therefore the geology beneath the surface, albeit at a much slower rate than the Andes, results in a dipping series of strata all the way from the Caribbean into central Venezuela. This differs from the horizontal deposition from where it was originally placed. So how does wrench faulting play into all of this, and what even is wrench faulting in the first place? A wrench fault, also called a tear fault, is a type of strike-slip fault where the lateral motion of two dipping blocks creates the appearance of a normal or reverse fault. I know that me just saying these words must not make much sense, and it's been a while since any of us have been over tectonics, so I made a drawing to help illustrate how this works. So we're going to start out with two different blocks of earth, Block A and Block B. Block B, this is our kind of what we've been looking at in the last slide. We have our Pleistocene sands and clay here. This is our cap of clay. We have our sandstone that acts as our storage unit for the oil, and then we have the early Pleistocene and older Miocene silts and clays down beneath it. And you have this sort of similar thing going on over here with A, just shifted over, and this line down the middle right here. is the fault line as viewed from the surface. So if you think back to earlier and what was said, with the Andes orogeny, it starts to slope down. We can kind of trace those lines coming down here. So we got, this is gonna come down, this is sloping down here, slopes, and there'll be more down here, but we don't need to worry about that right now. And let me just fill this in quick. All right. So same here, we have the early Pleistocene silt and clays. The cap, we have the sandstone right here in which the oil is held in, and then the Miocene silt and clays down below. All right. And you can kind of trace these over. This is looking at it at the outcrop view. If you were to look facing at it, same thing, fault lines here. And we're gonna do that same tracing. So if we look at the front of block B right here, we can imagine that these blocks are next to each other, like we're looking at them in outcrop view right here. We look at this and then we see that, or we can imagine that this is like how we'd see this block with it dipping down. And you'd imagine that the same thing would happen over on A, where this would come down to somewhere around here. You get this thick piece here that would go down there, that cap here, and then the sandstone down below. So I'll just fill this in. The sandstone, we got that same like Pleistocene silts and clays. We got the cap here, and then this other kind of corner piece here, that's some other rock type that we don't need to worry about. So if you look at it from this way, it looks as if it's a normal or reverse fault, where they're moving up and down relative to each other. But if you look at it on top, it looks like it's a transform fault, where it's just moving purely laterally from each other. And most of the time, and how they discovered it was through these outcrop view, and thought that it was that at first. But with the strike and dip, they needed to do that. And what they found was that with this wrench fault system, if you move this piece laterally, so just across, picture like you were going across the table in that direction, and this B over in this direction, sort of toward you, that the B, if you picture this on a three-dimensional plane, this one cap layer, it's kind of going to go this angle, and if you slide it toward you, it's going to appear higher in respect to the A, or if you slide the A away, it's going to appear lower. And now this was really important because they could find where this cap was in certain spots, but they couldn't find it in other spots. And it goes down below, thousands and thousands of feet below. And by measuring and finding out and knowing the depths of these different strata, they're able to kind of correlate and figure out where these caps were down beneath. And there's this whole series of faults. You can see it on the next slide, that in this northern Venezuela area, it's a really confusing section. There's so many different faults going on that it gets, all these reserves are just scattered all over the place. So this may still be confusing, so I'm going to try and simplify it as much as possible. Originally, Block A was much closer to the viewer and kind of this direction. And as it moved back this way, the cap, this black kind of piece that we're using to signal, got slid down in comparison. Due to the continuous movement of the Caribbean plate, these lateral fault lines occurred in Venezuela in order to facilitate the changing earth, directly impacting the oil fields underneath the surface. As you can see in the diagram, the faults are very complex around Venezuela, resulting in this very complex oil field genesis. This faulting style differs from many other petroleum fields, where the oil or natural gases are in one continuous layer. These layers can be bent, but many times it is a continuous or generally continuous throughout. Knowing the horizontal distance between these surface layers or examining outcrops and finding the distances between matching layers on either side of these faults has helped petrologists discover just how extensive this field was and how there are plenty of separate fields within the Venezuelan basin. As seen on this diagram, oil and gas gets trapped on the margins of these fault lines, with the wrench faults and some normal faults visible. The Cruz Formation clays are the source of the hydrocarbons, and they migrate up the stratigraphic column until the late Pliocene and Pleistocene clays create caps, forcing the sandstones of the Pliocene to become storage units for these natural gases. Due to an advanced understanding of the wrench fault systems in the area, petrologists were able to locate these reserves, allowing them to tap into the largest oil and natural gas collection on Earth.